In this example we will create and examine the PQ capability diagram of a wind park. Activate the study case 4.1 PQ diagram at 20 kV. Look at the grid tab. Here you can see the wind park. The wind park consists of 6 turbines. Double-click on a turbine to examine its parameters. You can see that this turbine has an active power rating of 2.5 megawatts. All turbines in the wind park have the same active power. You can also see the capability curve of the wind turbine. The red lines indicate the reactive power capability of the wind turbine at different levels of real power output. We can examine the capability curve in more detail. This dialog indicates that for each wind turbine a number of capability curves have actually been defined. The capability curve which is applied depends on the voltage local to the turbine. The overexcitation part of the characteristics are defined in the upper matrix. The underexcitation characteristics are defined in the lower matrix. The column headings refer to active power values and the row headings refer to voltage values. User-defined headings can be specified on the configuration page. Limits can be specified in terms of per unit or in terms of megawatts and the megavars. Notice the shape of the characteristic in the top right-hand corner at higher voltage levels. Notice that at the point of common coupling the nominal voltage is 20 kV. Having now observed the PQ capability diagram for an individual wind turbine, we will now create a PQ capability diagram for the whole wind park. To do this, we will use a Dpl script. Change to the tab 04.1 Start calculation of PQ diagram. The Dpl script can be accessed by clicking on the button. Click on the description page. Here you can see a description of what the script does. Return to the basic options page. Ensure that the number of steps is set to 100. Notice that the nominal voltage of the wind farm is set to 20 kV. The script will carry out a number of load flow calculations. During the load flow calculations, the active power values will be swept from 0 per unit up to 15 megawatts in a series of 100 steps. Execute the script. You can see that two characteristics are shown. The blue characteristic represents the required reactive power capability and can be adjusted according to the applicable standard. We will now adjust this requirement. Change this parameter in the script to 100. Notice that the overexcited power factor and the underexcited power factor at the point of common coupling are both set to 0.95. Execute the script again. You can see that now the requirement is that of a constant power factor reactive power capability curve, set to a power factor of 0.95. The red characteristic represents the reactive power capability of the wind park. You can see that in this case the calculated reactive power capability of the wind park is able to achieve the requirement. Activate the study case 4.5 PQ diagram at 18 kV. In this example, the voltage in the point of common coupling has been decreased to 0.9 per unit. Due to the low voltage, the power from the wind generators is transferred by a higher current. Therefore the loading of lines and transformers is higher. The maximum allowed loading can be defined in the script. Run the script once more. In order to prevent equipment being overloaded, the power of the wind turbines is reduced. A summary is printed in the output window, which shows that the maximum loading of the transformers is around 100%. Activate the study case 4.3 PQ diagram at 22 kV. In this example, the voltage in the point of common coupling has been increased to 1.1 per unit. Run the script once more. You can see that the reactive power capability of the wind park has changed. Notice in the top right-hand corner of the plot that the requirement is not being met. Reactive power compensation can be used to meet the requirement. In the grid you can find a capacitor. Double-click on the capacitor and increase the number of steps on the capacitor to 8, so that a reactive power of 2 MVA is introduced. Run the script again. You can see that with the reactive power compensation included, at high power levels the reactive power requirement is met.